Hello and welcome. Today we're going to talk about electric charge and electric force. Hopefully everything we talk about will be a review from what you guys learned last year about Coulomb's law. So let's get started. So the first thing to mention is that in electric charges we have two different types of charge. We have positive charge and negative charge. And these two charges attract to each other, while opposite or similar charges, such as a positive and a positive charge, will repel each other, and they'll push each other away. So opposites attract, and like charges repel each other. Second thing to realize is that charge is conserved always. So meaning, if we have an object that has a very, very positive charge, and then we have another object that has no charge, and we touch these two objects together, all of this positive charge is going to transfer to this object. So the sphere isn't becoming positively charged out of nowhere, but instead that charge is being transferred. And this is true of anything. Anytime an object acquires a charge, that charge has to be coming from somewhere because of our conservation of charge. So charge can't just magically appear. It has to come from somewhere. And this total charge that the object acquires can be found with the expression Q equals NE, where Q is just our abbreviation for charge. It's our variable that we'll use in formulas and everything like that. N is the number of charged particles. And then E is the charge of each individual particle. And so when we say charged particles, we mean either protons or electrons. And protons and electrons have a charge of plus or minus 1.6 times 10 to the negative 19th coulombs. And so electrons have a negative charge, protons have a positive charge. So this is how we can give an object a charge by contacting it between, or making contact between two objects. But we can also charge an object without any type of contact whatsoever. And this is called charging by induction. And the way it works is if we start with a sphere that is both made up of positive and negative charges so that it's completely neutral, and we bring an object close to it that has a very strong charge. In this case, let's say this rod has a very, very positive charge. And so what happens is that positive charge attracts all the negative particles in the sphere, and in return repels all the positive charge to the other side. So it separates all the charge within the sphere. And so then if we take, say, a wire or something like that and connect it to the sphere and then ground that wire, it causes all of the positive charge to leave. And it'll actually push it out of the wire, or down the wire out of the sphere. And so as a result, if we remove the wire and then we remove the rod, our sphere will be made up of nothing but negative, or predominantly negative charge. And so we managed to remove all of the positive charge from this object without making any contact with it whatsoever aside from the wire. We just brought a charged object near the sphere, and it pushed all of the positive charge out of the sphere. And so that's charging by induction. And so the last thing we'll talk about is our actual electric force. We mentioned in the very beginning that two objects that are oppositely charged will attract each other with a certain force. And so the force that they attract each other with actually obeys Newton's third law, in that these two forces are opposite but equal to each other. Meaning F1 will equal negative F2. So they have the same magnitude, they just point in an opposite direction. And so the actual magnitude of this force can be described using Coulomb's law. And Coulomb's law just states that the force will equal K times the charge of the first object times the charge of the second object divided by the distance between the two objects squared. Very, very similar to our law of gravitational attraction, where in this case our K is our electrical constant, or Coulomb's constant, which is equal to 8.9876 times 10 to the 9th newtons meters squared per Coulomb squared. And of course the units just come from the formula. But sometimes it's easier to express K in terms of 1 over 4 pi epsilon naught, where this epsilon naught is our permittivity of free space. And I know that probably doesn't mean a whole lot to you right now, but as we continue on, and especially with magnetism, permittivity of free space will become a lot more important. So just kind of keep it in the back of your mind for now. And our permittivity of free space is equal to 8.8542 times 10 to the negative 12th Coulomb squared newtons meters squared. And of course, neither one of these need to be memorized because they're both on your formula chart on the first page with all the rest of your constants. So then the last thing to mention about this is that this formula gives us only the magnitude of the force. And so when we use it, it's very important that we use the absolute values of our charges. If one of these charges is negative, we don't want to use a negative sign in the formula. Instead, we want to take the absolute value so that we always get a positive force. And so this will just give us the magnitude of the force. And so then once we have the magnitude of the force, it's up to us to go back and determine the direction afterwards based on the charge arrangement. So, for example, if we have 3 charges, let's say we have a positive charge, a negative charge, and then a third positive charge. And so we can label these charges as charge 1, charge 2, and then charge 3. So let's just look at charge 2 for right now. We know that charge 2 is going to be attracted upwards, and it's going to be attracted to the right as well. And so we can call this our force 1, 2, because it's the force created between particle 1 and particle 2. And then this is force 2, 3, because it's the force created between particle 2 and particle 3. And so we can use Coulomb's law to find these two forces using K Q1 Q2 over R12 squared, where R12 is just the distance between Q1 and Q2. And then do the same thing for the second force, K Q2 Q3 over R23 squared. And so this will give us our two forces, but after we find the magnitudes of our two forces, which again, we use the absolute value of our charges, it's up to us to realize that our particle has one force going to the right and then one force going perpendicular to it straight up. And so then from there, it's up to us to realize that our resultant is going to go right between the two and can be solved using Pythagorean theorem. F12 squared plus F23 squared. And so electric force is just a force like any other force that we've dealt with all year long. And we can manipulate them and find the resultant of those forces by any means necessary, whether it's Pythagorean theorem or breaking it up into components, etc., just like we've done in the past. Anyway, I hope this is a good review of electric charge and electric force.